So the key idea is we provide a network with an input 2D layout where the locations of the furnitures and cars and so on. And given that the 3D generative models generates a 3D scene that respects these input 2D layout.
Welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. We host early career academics and PhD students to share their cutting-edge research in computer vision, machine learning, and everything in between. I'm your host, Itzik Ben Shabbat, a researcher by day and podcaster by night. Let's get started. Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. Today we will be talking about the paper CC3D, Layout Conditioned Generation of Compositional 3D Scenes. This paper was published in ICCV 2023, and I'm happy to host the author of the paper, JJ Park. Hello and welcome to the podcast. Can you introduce yourself?
Hi, thank you for the invitation. I'm JJ Park. I'm currently an assistant professor at the University of Michigan in computer science and engineering. And previously, when I wrote this paper, I was doing my postdoc at Stanford University, working with Leo Gibas and Gordon Weschtheim. And even before that, I was doing a PhD at the University of Washington, and schooling for the rest of my life.
Oh, you move around.
Yeah, I moved around mostly in the West Coast. From LA to Seattle to Stanford, and even before that, I was in South Korea, and now I moved to a very different place in Michigan.
Very nice. And who are the co-authors of this paper?
Yeah, so the student author of this paper, who done a lot of work, is Sherwin Bachmani. Who I met through when he was doing an internship with me at Stanford, with me and Despoina, who was also a postdoc with me during my postdoc at Stanford. And there's Xing Guan, who is a PhD student of Andrea, who's the last author. They're both in Simon Fraser University in Canada. And then there's the other authors, Gordon and Leo, who was my postdoc advisors.
All right, so let's get to it. In a TLDR kind of format, in 2-3 sentences, what is this paper about?
Yeah, so the TLDR, while most generative models try to generate 2D or 3D scenes at a single shot, even if it's compositional, we try to separate the process into, two separate processes. One is the planning phase, and the second one is a generation phase. So this paper is mostly about the second phase, where we assume that you already have the plan of the generation, the compositional generation, and we focus in the latter half, which is to generate a actual 3D scene based on the floor plan. And we assume that these plans could be generated by, manually generated by humans. You can imagine drawing a picture, a square of your, floor plan and add furniture as you wish. Or you could imagine using AI programs to generate these floor plans.
Right. So let's break it down a bit, right? So your input is basically an image of a floor plan, right? So a floor plan is basically, some room, let's say a rectangular room design where you have like different spaces allocated for different types of furniture, right? So in a bedroom, you would have a bed, and you would have a nightstand, and you maybe have some cupboard or something like that. And given this input image, the output that you want is actually like this 3D scene where you actually have 3D models placed inside a room of the bed, like a 3D model of the bed and a 3D model of the nightstand and a 3D model of the cupboard or whatever that is, right?
Yeah, exactly.
Yeah, and the way a human would do it, right? He would just look at the floor plan and say, okay, the table goes here, and I will place this, go to some, either design a 3D model or go to some data bank, and they would just place it in. And what you guys are doing, you're saying, well, let's let the generative model do it, right? Let's give it the input floor plan and generate the 3D scene. This is really fascinating. But before we get down to the bits and bytes, so what challenges are in this space? So what problems is this paper addressing?
Yeah, so there are largely, there are many problems, many challenges in generative model, especially in 3D generative model. There has been a lot of progress made in single object generation, but there are still huge challenge in multi-object compositional scene generation. One of the big challenges of that is that there is, there's multiple decisions to make. The first decision is where to put these objects in. Like, it's a more structural and spatial decision. And the other decision is, how does actually these objects and scenes look like? It's more like traditional generative model. Like, how does this object look like? So we try to separate these challenges into two, and then make it easier so that we don't have to do these two challenges at once. Another challenge in 3D generative model literature is the representation. So what is when you want the AI system to generate 3D objects or 3D scenes, what are we actually generating? Are we generating points, mesh, voxels, or implicit representation, or what is it? We extensively explored some of the most common recent developments of these 3D representations in generative models, and we claim that for our task, and perhaps for many tasks with similar generative training data, our proposed representation is superior than previous methods.
Yeah, these are really great challenges in the field, right? So I think choosing the right representation is already half the problem, right? Because unlike 2D, where you have an image, right? You have the pixels, you know what you get. In 3D, it's like, well, is the mesh better? Is it radiance field? Maybe implicit function, right? It's always a big question anytime you approach like these kind of problems.
And even within implicit representations, there are many choices these days. There's like hybrid representation between explicit and implicit, and exploring these areas is like really hot these days.
Yeah, I couldn't agree more. It feels like if we only used to have like three main representations, right? Voxels, meshes, and point clouds, and like implicit were kind of there, but nobody was using them. Now it's like shuffles everything up, and there's like a mix of everything. Yeah, really interesting challenge. But tell me, but why is this an important problem? Like, what are kind of use cases and applications that this problem like can appear in?
A lot. One obvious scenario is for content creators in, designers or game creators. Imagine you want to create a house for display in like digitally. You want to sell a house. Okay, I want these objects to be here and there, and instead of manually putting in selecting furnitures into this scene, you could automatically get these nice looking furnitures there. Another really nice application would be providing training environment for autonomous agents. So we have some demonstration on the Kitty dataset where we provide a similar floor plane like concept from top-down view. So it's called bird eye view. So we provide a 2D representation of the bird eye views, locating, okay, this is a street, this is cars, and so on. And from that, we generate a 3D scene where you can move around within the scene. So potentially, this could scale up the generations of virtual 3D scenes that companies or researchers can use it for training their self-driving models in the future.
Right. Yes. Super interesting applications. And I don't know if you avoided it intentionally or not, but I guess it falls under content creation. But right, I think the metaverse, right? If you want to create spaces for people to meet up, right? It's like kind of like a huge buzzword, but I think this is like a huge thing that could be really beneficial, right? You want to design your personal space in your personal metaverse environment. So you can use this kind of, okay, I'll give it a floor plan. I want to be in a bedroom or in the office or something like that.
I would call it democratization of 3D content generation. Used to be, the area for the experts, and now we slowly moving towards space where everyone can generate nice 3D scenes.
Yeah, amazing progress. So now, but if you had to kind of distill the specific contribution of this paper to the space, so what is the main contribution of this paper?
Yeah, the main contribution, I think, can be split into two. The first is our suggestion to separate the generation process into two phases. The first is the planning phase, and the second one is the actual generation phase. And we find out that empirically shows that if you separate these two, it's much easier. And it's different from the previous works that try to generate both these scene structure and the appearance together. So that's one of our big contribution. And another one is that, it's kind of follows the first contribution, is that it's very easy for people to control the generation process. So a lot of previous works, if you've been following GAN works, it's the data, the output data that you get could be random. So you just randomly sample realistic looking scenes or images. But in our case, we try to be very controllable. So anyone can draw the 2D layouts of the rooms that they desire. It's very simple, just some squares with squares and circles in here and there, and you label, okay, this I want it to be desk or bed and so on. So that will give you a lot of control of what type of scene you want to generate, as opposed to a generative model that just give you a nice, realistic looking scenes, but you don't have control over the specific furnitures of that scene. The last contribution, I would argue, is the improvement of the representation. As we briefly discussed, we use the neural implicit representation with some hybrid of extrinsic representation with the grid structures. So the features live in the grids, and then you can interpolate that to get the continuous neural field. And we find out that the previous ways of representing these neural fields have some disadvantages in representing compositional large-scale scenes. So we propose a really simple method to overcome these limitations.
Right. I can't wait to dive into the details of all of these stuff. But before we do that, let's talk a little bit about related work, right? So think about the novice PhD student, first year, just started off, coming to read your paper. Which other papers should they read first in order to kind of get the ball rolling?
Yeah. I think students interested in this type of research should first read STAGAN. STAGAN 1 and STAGAN 2. They pioneered the mechanism of conditioning code to the generation process, which is through by modulating the features of the intermediate activation features of the neural networks, which most of the papers these days are based on. Got inspired, at least inspired by. But the STAGAN the series of Stockgan papers were operating on the 2D image domain. And there's obviously benefits of generating 3D scenes. You can rotate it around, you can edit it better in the 3D scenes, and so on. So for the past 2-3 years, there has been like enormous progress in the literature on 3D generative models, especially 3D GANs. These works typically use this 3D representation called implicit neural representation, introduced by one of my papers called DeepSCF. I also recommend you reading it if you're new to this field. And using this representations, there are a series of works, including PyGAN, Drafts, and GSN that all do GAN training on the 3D domain. So what they do is they first sample a random 3D scene, and then they randomly sample a camera viewpoint to render this 3D scene from. And then they just make sure that from all possible viewpoints, these 3D scenes look realistic. And recently there has been attempt to make it very efficient, pioneered by a paper like EG3D that uses a grid-based representation to model the implicit neural field, which proved to be efficient and high quality. So these are the related works that I recommend that the students new to this field to read.
Yeah, great. I'll make sure to put links to all of these relevant references in the description. I have to say, DeepSDF is one of my favorites. I even remember walking around CVPR, seeing that paper on the poster of that paper. And I remember like it was the same conference. There was another one that was very similar, but did it with like occupancy network, and you guys did the sign distance field. It's a really great paper. I really love it. And I even had like
Yes, I should have mentioned the occupancy networks. That was the concurrent work that introduced the neural implicit field.
Yeah, and like these.
There was another, yeah.
There
from,
was,
from Simon Fraser University. Yes.
Yeah, all of these papers kind of launched this field into this spiraling. Like there's like so many papers that came afterwards trying to improve it. Like works from Jeroen Lippmann's group in Weizmann Institute that kind of played around with the way you define the loss and how you improve and do like geometric initialization and all of these and then sirens and all of these kind of works that followed it kind of really showed the strength of this representation. It's one of my personal favorites from the recent years. But okay, enough about related work. I'm really curious to see what you did in this paper, right? So let's talk about the approach. So tell me, what did you do and how did you do it?
Yeah, so our input is, as I said, the 2D layout. And the major task is how do you get 3D from this 2D layout? And if you have a computer, if you have a monitor, please look at figure 3, which shows the architecture figure. What it basically does is that our main backbone, which is the conditional Stockgan, takes this layout image and outputs a feature map. And within the Stockgan, an important point to note is that the Stockgan is modulated by some latent vector, which decides the style of this scene that is about to be generated. Because there are so many ways that you can generate 3D scene respecting the 2D layouts. Okay, so 2D layout in, 2D feature maps out by the conditional Stockgan architecture. And what we do is we take this feature map and we reshape it and create a feature volume. This is slightly different from previous approach like EG3D that tries to reshape it to make a triplane representation. It's difficult to say it in words, but essentially what they do is they place 3 planes in the XY, YZ, ZX axis, and that way they represent the scene. But as I will probably have to explain later, we find problems in this representation. So instead, we took a simpler approach, which is to just reshape the 2D feature map and make it into 3D. So there's the number of features does not change, but you simply change the shape of your tensors to make it a feature volume. And once you have that, that is our 3D representation. So you can query a continuous point within this feature volume, and then you do trilinear interpolation to get the query feature from that point, which is then passed to an MLP layer that outputs the density and the color volume, which is typical in NeRF. And using this mechanism, we can render the scene from any particular camera viewpoint using volume rendering. And this volume rendered image output is then passed to a discriminator that tells you, okay, is this real or fake image? And we optimize our generative model so that the discriminator is fooled to think that this is a real image.
Yeah, I just want to add one thing. One of the things that I really liked about so when I came to read the paper initially, until I read the approach part of the paper, I only then kind of realized that, wait, you don't have a paired like floor plan to 3D kind of one-to-one correspondence, right? This is a completely different case. You have a floor plan, right? And then you have this and you want to generate these 3D scenes, but without this pairing. And the way you do that is using the GAN, right? So the GAN, you're basically asking, is this generated 3D model that I created, if I render it from one image, if I render it from one camera position and view direction, does this look real? Like, is this an image from the distribution of all possible 3D scenes that are kind of from the data set, or is this a fake one that I just generated? And that was really nice, like, because to me, the first thing I would do is, well, if you have a one-to-one, you just do kind of a reconstruction loss and you're good. But here, no, you don't have a reconstruction loss. This is a GAN loss.
Right. Yeah. I kind of got used to that, so that's why I didn't mention it. For me, it's kind of natural, but you made a really good point. Like, what's fascinating about these, I think this paper and also the field in general, is that oftentimes you don't need camera pose, like ground truth camera pose. You don't need correspondences. So here, as it's say, we're just given a two separate set of data set. One is the list of, the layouts and the list of 2D viewpoints. We don't even have multi-views. We just have 2D viewpoints. And then from there, you just process the 2D image to generate 3D model. And then you render this 3D model. And then you just require that, okay, needs to look realistic.
Right. Okay, let me recap and go over it again, right? Because this is like a lot of detail and a lot of stuff to take in, right? So you got your flow plan, you're putting it in through this architecture, you're getting kind of features, you're and you're conditioning it on this kind of vector, right? That basically controls the style.
Yes.
Yeah. And then you're reshaping it, right, to be like this volumetric representation of features. And then in this volumetric space, you can sample every point to get the density and the color. And now you can render it from any pose that you want to get like a final output image of that 3D scenes that you just generated. And actually, I guess we haven't fully discussed the next part, right? So how do you train this? So what are the losses?
Yes. So I think there's one minor error that within your explanation. We do not densely sample the feature volume during rendering. We sample it as on demand, right? You have a viewpoint and you just shoot a ray, and then you kind of randomly sample the points on the ray following the volume rendering equations by, Nerf and other papers. So that was like a minor thing. And there are generally two major losses. The first is the adversarial loss. Okay, does it look realistic when you render it from arbitrary viewpoint? Okay, so if you have this loss, okay, it could generate something realistic, something very nice. But the problem is that this network can simply ignore your conditioning. So it could just put your input 2D layout in the garbage can and then just, I want to generate something realistic. I don't care about the input. I'm going to just set all the weights on these encoder layer to be zeros, and I'm just ignoring everything. In practice, it doesn't happen. It doesn't work that extreme. So it does seem to respect the input layout. We believe that is some inductive bias that comes from the same location of the 3D scene and the layout. So it does seem to respect it to some extent, but we often observe that some furnitures disappear in the 3D scenes. So to better enforce the alignment between the generated 3D scene and the input 2D layout, we introduce another loss, which is the layout loss. How it is implemented is also pretty simple. So from the feature volume that you got by reshaping, you simply sample random points along the rays that goes from the top to the bottom. So it's the top-down bird eye view. You're simply doing, say, orthographic projection, and doing that, you're sampling some random points along the ray, and that gives you an image because it's orthographic projection, right? And using that, you put that into the star-GAN discriminator we use for the GAN training, and we attach a decoder layer so that we output the semantic segmentation of this floor plan. So I'm going to repeat that. So you have the feature volume, you generate an orthographic image from top-down view, and then put that into some unit architecture to get a segmentation of this floor plan. And because we know the ground truth, which is our query 2D input layout, we can compute the cross entropy loss between our predicted segmentation and the ground truth. And this is another layout loss that we use to make sure that the layouts are respected by the generation process.
This is done pixel-wise, right?
Yes. No, this is yes and no. I mean, it depends on how you define pixels, but it's on the feature volume, the slice of the feature volume space. Yeah.
Right. But so you're projecting it, right, onto the, I don't know, ZX plane, I guess, if Y is up, right? So you're kind of projecting everything. You're getting an image, and then you're taking that image, comparing it to the original floor plan, and you're doing cross entropy, right? Between those two. Right. So this is pixel-wise, right?
Yeah, I think you're right. Yes, okay. Yes.
Okay, that's really nice, because let me just quickly recap what you were saying, right? So you were saying basically, if you just feed everything without this new floor plan semantic loss, right, then you would just get nice 3D scenes that kind of follow the floor plan, but sometimes would lose a chair or some other component in the scene, and you kind of want to enforce that the floor plan is an important thing that the model needs to follow. And in order to do that, you're kind of now basically penalizing the model if it deviates too much from the original floor plan, right? You're basically doing this, the semantic kind of loss that kind of forces the output scene to have all of these pixel level class correspondences, which is really nice. It was surprising that you weren't getting it originally, but this original loss, it's nice that it's putting it back in there. And I guess like when I was reading it, what I was thinking was, well, maybe if a component is too small, then it doesn't have a lot of, if you encode it now into features, it doesn't have a lot of representation power. So yeah, it makes sense that the network kind of maybe ignores it because the overall kind of takes over, right?
Yeah. I think the readers should look at figure 5 that shows that, some without the loss, it loses randomly some objects, and with the loss, it has better behavior.
Yeah. I think in the results, it usually kind of keeps the main item, I guess, like in bedrooms. I know from what I saw, correct me if I'm wrong, but like in a bedroom, it keeps kind of the bed, right? Because it's the main thing that it's looking at. Did it happen with and without the loss anyway, right? Did it kept the bed, but it kind of put other things away, right?
Yeah. It kind of missed the small ones, oftentimes. Yeah.
Interesting. Okay, this is a great bridge to start talking about the results, unless you want to, there's something we haven't covered in the method.
I think the representation we haven't covered thoroughly.
So let's talk about the representation a little more.
Yeah, I think if you look at figure 6, we show like kind of history of these neural implicit representations, different methods of that. So what this neural implicit representation does is that you can query an arbitrary continuous coordinate and get the feature out of that. And the original this implicit method, proposed by Despoina and others, and Nerf, they use an MLP to interpret this coordinate XYZ and output a feature. And because it's an MLP, and this MLP has to have information of the entire scene, this MLP has to be very large. And the problem of that is when you try to render a scene, you're sampling a lot of points along the rays to do volume rendering, millions, orders of millions. And for each of them, you're going to put them into the gigantic MLP to do this rendering, which makes it quickly invisible to compute because of the resources. So people have been trying different ways to amortize this computation. So they want to do, they amortize the compute in the early stage and then have a small MLP in the later stage. So an example is the floor plan based features in the GSN. So they have a 2D feature grid on the floor, which is computed a priori. And then when you query an XYZ, just project these point to these XZ plane, and that to get the feature using bilinear interpolation. And you concatenate the feature with your y-axis and then put that into MLP. And your MLP could be theoretically be smaller, but the problem is that your MLP still need to model the entire column of the scene, which could be still expensive to model by MLP, and your MLP has to be still large. And the third representation introduced by EG3D is triplane, which is very interesting because it does not try to densely represent the neural field. What it does is that it has 3 planes in each 2D axis of your coordinate system. And then when you try to query an XYZ position, you project them to 3 of these feature planes with bilinear interpolation, and you concat or add them and then put that into an MLP. And you can see that there are a lot of information that are pre-computed by the process of generating this triplane. So your MLP can be really, really small. So you're kind of amortizing the computation in the early phase of your generation process. But the problem is that as you're triplanes becomes bigger and bigger, it becomes more like just XYZ coordinates. Because if you think about it, in these triplane models have this one plane that represent the entire volume of XZ plane. So if you imagine if your scene is very large, very long, then all of the points in this line will be projected to the same feature in your, say, XY feature plane. Then this cannot have all this information there. So what it ends up being is that it just gives you the coordinates of these locations. And essentially, if your scene is larger, then you need to have a larger MLP. Another problem of this triplane representation is that the process of generating, which is the CNN, does not have a proper geometric inductive bias when on these triplanes, because these triplanes have different geometric meanings, but they do just concatenate them and generate them as concatenated features. And if you do convolutions on these triplane features concatenated, each filter will be looking at locations that are totally different, and it loses geometric meanings, which is a huge downside, I believe, of triplane representation. And in order to keep this geometric inductive bias, at the same time, to minimize the computation, we introduced this extrusion operator, which is a fancy word for reshaping a 2D image into a feature volume. In this case, when you apply the 2D convolution on this feature grid, because you're just expanding your 2D image into the feature volume, the features around the neighborhood of these convolution filters are shared, and they have geometric meaning of that. And we, in our experiments, we show that our hypothesis is indeed correct, that our method generates more geometrically reasonable scenes and is pretty computationally cheap to generate as in the triplane method. Sorry for the very long explanation.
No, it was a great explanation because well, first of all, yeah, I think it's a very difficult problem. Like, these things becoming unfeasible when you're sampling so many points, like millions of points, and yeah, a good way to kind of find a way around it to sample or represent the scene, the volume, is a really, really important thing to solve. And this representation that you guys came up with, I think it does that really elegantly, right? It's very simple. It's very fast, right? It's very intuitive. And it has the geometric meaning, and it's not computationally expensive. So you're kind of winning on all sides here.
Yeah. And the downside is that if you're trying to model very large scene, it also can't do it because it's expensive to store this feature volume. Your feature image should be the channel dimension of your feature image should be very large to transform it into feature volume. So we still haven't solved that problem yet.
Right. It kind of turns into, you can kind of parallelize it to voxels, right? It's not a voxel, obviously. It's kind of like a feature grid, but you still have a grid, right? So your resolution is kind of limited by the grid resolution, right?
Yes.
Yeah. Interesting. Okay. So now let's move on to the results section of the paper. So you got your method, you're taking your flow plan, you take your random vector, you're putting it in, you're getting a nice 3D scene with your kind of nice special representation out. How do you evaluate this thing?
Yeah, so our experiment is actually quite simple. We randomly sample the floor plans in our data set in 3D front. We use 3D front for indoor scenes and Kitty for outdoor scenes. But for indoor scenes, we just provide the randomly sampled existing floor plans. And then we generate the 3D scenes, and we also randomly sample camera viewpoints to generate images. And we do that for all the other methods, except that the existing methods don't rely on this 2D layouts. So we had to train a unconditional version of these ones, and these comparisons, EG3D, GSN drafts, all generate their images without the conditioning to the input layout. And then we compare the result. So all of these methods generate images, a set of images we generate, and then we compare the realism of these output images using the standard metrics such as FID and KID, which shows you the similarity of the distance of the distributions between a set of images. So we compare this distance of distribution between the generated set of images and the ground truth real set of images.
Right. So you basically, obviously, like if it was a perfect solution, right, then you would get a very small distance between the distributions of generated images and original dataset images. But obviously, no method is absolutely perfect. So there is some difference between those distributions. But your method kind of outperforms all the previous ones.
Yes. And qualitatively speaking, you can see this in our website, but we show some video comparison between our methods and the existing works, and not only there's difference in the quality of the images, but there's also structural differences. Like EG3D tends to generate scenes that are kind of copy and paste over in their axis, because there's a special meaning of the zero origin in their axis. So they tend to generate some hallucinations or some weird artifacts there. And ours are, I think, quantitatively and qualitatively better than others. We also show comparisons on the kitty for the same task, which is the outdoor scenes. So you can see the example of the conditioning layouts and outputs in our supplementary material, and also on the website as well. Another experiment that I want to point out is the ablation study. So there might be people that argue, okay, your algorithm works better because there is a conditioning, and is strictly more information than the unconditional methods use, like EG3D or Giraffe. So how do you know that your method is better? So to protect against this argument, we conduct an ablation study where we fix everything. We use the exactly same of our method, but use just different representation. So in table 2, we show that when we keep our algorithm but change our extrusion algorithm representation into the GSN's 2D floor plan representation or triplane representation, you can see that our representation performs better. Shows that it is not just coming from the input information, the more extra information we're giving, but it is our algorithm and the representation that also gives us the boost of performance. And we also show that the layout conditioning is important, increases the quality, and also that without the layout consistency loss, which I introduced just before, the loss improves the quality of the generation.
Right. I think so. Yeah, I think all of these, like, obviously without the bold numbers, we don't have papers in this day and age, right? But I think what I like the most about the papers is actually some things about the ablation study. And in this particular paper, I really liked how you kind of separated it to show, the representation works on its own. But what I found really interesting was the fact that, well, to me, adding the floor plan, that's not a lot of more information, right? But then I thought about it and it was like, well, but maybe it is, right? Because it kind of tells you how a typical bedroom would look like, right? Or a typical I don't know, other kind of room would look like. And that's a very, very strong prior to add, right? This is a very strong information to add that you like, if you, well, technically speaking, you have that information in your data set, right? You could generate a flow plan for every data point, right? It's just a projection from the top. You have that data. If you have the scene, you have the data. But the fact that you can kind of disentangle it and feed it separately, right? You're basically saving the model the need to implicitly model it or kind of take that into account. So this is one of the thing that I find really interesting. So the fact that you take the floor plan, you feed it separately, and that really boosts performance. That's really nice.
Yeah. I thanks for mentioning that. I forgot to mention this important fact that it confirms our hypothesis that it's beneficial to separate the process into two: the planning and the generation. And if you have no conditioning of the layout, then you're doing this process at once, which is strictly harder than just focusing on generating nice 3D scene given the planning.
Right. Before I ask the what are the failure cases question, I think we haven't discussed the input vector that you're kind of putting in, right? Because basically that vector, that controls the style, right? So if it's a bedroom, right, it would control, I don't know, the color of the bed sheets, right? And all of these kind of things.
Right.
So what are the fail cases in that context?
Yeah, so that style code generates, it decides the style of the scene. So it's a one vector that determines the style of the entire room. So we cannot do a per object style changes, which is, a limitation of our method. We need to change the entire scene at the same time. And another consequence that comes with this is that it is oftentimes difficult to do translations and rotations or removal. So certain editing activities in the input layouts. Because these styles are so mingled to each other, changes of your input layouts often result in the change of the style, even if you don't change the style code. So disentangling the styles of each object is one of the interesting feature work.
And the opposite is also something that happens, right? If you change the code, you might change a little bit the layout, right? Or is that not happening?
No, that we didn't observe that happening, actually. Mm-hmm. That part is pretty robust.
Okay.
If you change the style code, it really changes your scene without changing the locations. I think you can see that in figure 12 of the evaluation study that shows it works really nicely.
Nice, really cool. Any unexpected results that you encountered?
Yeah. So even with the layout consistency loss, the networks tend to ignore small objects, especially if it's very large. The scene is very large. So if you look at figure 16 of the supplementary materials, which shows this kitty scene conditioning, and you can see there are a lot of objects in the layouts, and you can see that it tends to ignore cars a lot. Yeah.
Kind of important.
Yeah, cars are important. So, yeah. So this is, I think, the major limitation of the method.
Yeah, and this is like laying the grounds for future work, right? So yes. It's clear that there is still work to be done here and still research to do. And this is a great bridge for our next part of the conversation, the conclusions and future work section. So how do you see the impact of the paper going forward? And are there any interesting papers that followed or should happen if they haven't been published yet?
Yeah, so I think it sets the tone for these two separate processes for generation. Right now, I think a lot of people are just focusing on generating everything from one go. If you look at, like, say, diffusion models, 2D diffusion models, video diffusion models, they don't try to, add structures to their generation. And I think CC3D paper kind of introduced a nice platform of thinking to the generation community, that separating your generation process into structure generation and the appearance and geometry generation is beneficial. And there's many ways to do this, many ways to achieve this. We tried 2D layouts, top-down view, but oftentimes the top-down view is not applicable. Then people could think about conditioning on other modalities like voxels, point clouds, and whatnot. Or even bounding boxes. If you think about generating videos, you could think about first generating the bounding boxes, and then the movements of the bounding boxes, and then generates the actual videos, for example. And I think there's just a lot of exciting things to explore in the future. Yeah,
I couldn't agree more. And I think when I was reading the paper, I was like, oh, cool, another GAN paper again, after all of this diffusion chaos that's been happening recently. And I think the main downside of diffusion models, like most of them, the popular ones, is that you don't have the same level of control that you do, that is very well explored in GANs. And I think this is another interesting direction to continue to explore on. Can we kind of have the benefits of both worlds somehow, right? Have the quality of diffusion models and the controllability of GANs, and kind of fuse that into a single kind of research work. Because you don't see a lot of GANs anymore, just because, it's not sexy, but they have a very, very strong case why you should use them. This is a great example of that.
I believe that the depth of the GANs are greatly exaggerated. I think it has a lot of potential, and it's very flexible in terms of loss functions. Diffusion models have these reconstruction losses that are oftentimes harder to achieve when there's missing data and stuff. But GANs, you just say, okay, I want it to look realistic, and you can use it for very flexible cases. Where it's difficult to design even the loss functions for. So
really cool. A lot of interesting future works to come.
Yes.
Great. Okay, so this brings us to my favorite part of the podcast. What did reviewer 2 say? Can you please share some insightful comments that you had in the review process?
Yeah, I think the main complaint from them was that there are missing objects, and we didn't show the kitty result very well, which made us to add the kitty results more, and then rebut about, okay, there's missing objects, and we had to come up with the numbers. Okay, how many of them are missing, and then with what probability, the IOU numbers and that kind of stuff. So, it wasn't too difficult to defend, I think. It's just that
I mean, that's a very interesting comment by the reviewer, right? Like, they noticed there are missing objects, and you noticed there are missing objects, right? You didn't try to hide it. This is one of the limitations that you mentioned up front. But I think, like, for future work, it would be really interesting to kind of quantify and have a good way to evaluate, well, how many are missing, and like maybe even more, right? So obviously that made the paper better, because you kind of had to address it for the reviewer, and you kind of update the paper, and now there's like a clear thing addressing the missing objects, which on their own are a very interesting research question, right? Like, what do we do with those missing objects? How do we fix them? Like, should we fix them? Because if you're matching the distributions well enough, right, then why are they gone? Maybe they're not that important. Well, it's like a lot of I mean, for sure they are important, right? They're in the original layout, so they should be there. But why? These are all these kind of questions that kind of spark the next project, right? Like, why is it missing? Why are they missing? Why is it missing those? Why is the model not able Is it a number of parameters issue? Is it an architecture issue? Is it like a schematic, like overall approach issue? My intuition, by the way, tells me that these missing objects are just because of the size, right? When you're encoding it, if they have a small size and you don't get a lot of pixels, and you have like a big object that's taking up a lot of it, then that might be the thing. But I don't know. This is just my guess.
That's quite possible, I think. Yeah.
Cool.
Right.
All
so
right.
instead of doing like segmentation loss, we could consider like detection loss. There could be smart things you can do, I think.
Oh, cool. Yeah, I haven't thought about detection loss. Yeah, detection loss, or maybe some, I don't want to call it hard negative mining, but kind of weighting the influence of the different objects. Like if it's a small object, it should appear more or have like a stronger loss on top of it to kind of say, no, you have to, even if it's small, you have to consider it in the loss. It's important. It's not less important.
Yeah, it might be interesting topic to study in fairness in AI.
Yeah. Don't discriminate against small objects. They're important too.
Yes.
JJ, thank you very much for being a part of the podcast. And until next time, let your papers do the talking.
Thank you very much, Itzik. It was my pleasure.
Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.